Hello, I want to take you through reaction quotients, how to calculate them, and how to use them to predict if the stuff you put into a beaker or a test tube is already at equilibrium, or if the reaction is going to proceed in a forward manner to reach equilibrium, or if a reaction is going to proceed in a backwards manner to reach equilibrium. Remember that reactions can proceed from left to right in a forwards way, or from right to left in a reverse way, and we'll see how that happens here. All right, so let me show you how you calculate Q. The reaction quotient is abbreviated capital Q, and that uses initial concentrations. So those are the concentrations you put into your test tube, okay? The equilibrium constant, K, and I put a little EQ there on my K, uses equilibrium concentrations. So it's products over reactants, but it uses the equilibrium concentrations. So you initially put some stuff into a test tube, you can calculate Q, and then after it sits there for a very long time and reaches chemical equilibrium, then you measure the concentrations and then you can calculate K, for example. All right? So there's a slight little difference there. Now this is used for predicting the direction of the chemical reaction if you don't have something at chemical equilibrium. And we're going to look at this ratio of products over reactants to help us think and rationalize in which direction a chemical equilibrium goes. Okay? So if you have a reaction that you calculate the Q and it's exactly the same number as the equilibrium constant, it means that you have the right number of products in concentration with the right number of reactants concentrations, and so the reaction is at equilibrium, and the reaction is not going to have to react to the right or to the left to reach chemical equilibrium. There's just going to be a backwards and forwards reaction as you normally always have at dynamic equilibrium. Now, if Q is greater than K, the reaction is going to go left. Why? Well, you have too many products, okay? Your quotient, or that ratio, is too high because the product's concentration is too high, right? That number in the top of the fraction is just too high. So what you need to do is reduce that top number and maybe increase the bottom number, right, to get that fraction to become less and equal the KEQ. So what that means is the reaction goes left. If Q is less than K, the reaction is going to go right. Why? Well, Q is too small of a number because the reactance is too big, okay? The number in the bottom of that fraction, if it's large, is going to make that fraction small, and Q is going to be very small. So what do you need to do? You need to change the number of reactants and products by reacting to the right, and if it reacts to the right, then it's going to create that ratio that's correct, okay? Let me show you another way of visualizing this. This is a graphical figure from the OpenStax chemistry textbook. Check the description and the link of this YouTube video below if you want to jump right in and read this chapter, okay? And so it's more a graphical representation of what I just talked about instead of looking at the math of a fraction, okay? So we've got SO2 in equilibrium with SO3, and there's some oxygen in here, okay? And let's look at the left graph, okay? The left top and the left bottom. Let's look at that left side here. So the initial concentration of sulfur trioxide is equal to 0, okay? And so Q, we can calculate this, is equal to products over reactants. So if we plug everything in, we don't have everything, but we do have a 0. If we square 0, we get 0. 0 divided by whatever other those numbers are is going to be 0, right? So Q is equal to 0. Now, if you look on the left circled green here, you can see that Q is 0. That's like on the bottom of the graph, and that's less than K, which is, I don't know what that dotted line is, it's some number, right? So Q is less than K. So what that means is the reaction is going to go right to reach equilibrium, all right? And if you look at the top left graph, you can see that the sulfur trioxide starts at 0 and it slowly increases in concentration over time. The only way to make concentration of SO3 if the reaction proceeds from left to right. Okay, if the reaction proceeds from left to right, then it's going to produce more sulfur trioxide, and it's eventually going to reach, the Q value is eventually going to reach the K value, and then it's at equilibrium, okay? So think about that. When a reaction proceeds from left to right, you're reducing reactants and you're making products, okay? And then at some point that ratio right? There's some squares and stuff in here, so it's kind of complicated, eventually equalize at the equilibrium constant, okay? All right, and so that's summarized here, right? If Q is less than KEQ, the reaction goes right because you have too many reactants. So that's what we just saw. Now let's focus in on the right graph, all right? Here, the conditions are such, and it's circled here with that orange circle. The sulfur dioxide and oxygen concentrations are equal to 0, okay? And so we're focusing in just on the right pair of graphs here. So let's go ahead and calculate Q. Q is products over reactants. Now we don't know what the other concentration is, but we're dividing by 0 squared times 0. Whenever you divide by 0, you're going to get infinite on your calculator. And so Q is infinity. Q is definitely greater than KEQ. You can see how that Q is like asymptotic. It's off the graph because it's so big. It's infinite, okay? So if Q is greater than KEQ, which way does the reaction go to reach chemical equilibrium? Well, the reaction is going to go left to reach equilibrium because you don't have any reactants, okay? So if you look at the I'm calling them reactants. So if you look at the chemicals on the left side of this equilibrium, they start at 0, but then they gradually increase in concentration, okay? And if you look at the SO3 concentration, it starts out high and it gradually lowers, okay? At some point, the ratio, the quotient, right, is going to be equal to the equilibrium constant, and the concentrations stop changing and it remains at equilibrium from that point onwards, okay? That is shown here on this summary graph, highlighted in orange. If Q is greater than the equilibrium constant, the reaction goes left because you have too many products, okay? And my study tip for you here is just please read the textbook. Learning and language and so on is all in that brain chemistry for the helpful synthesis of knowledge, okay? So the more words and the more different ways of seeing this explained really helps you conceptualize and understand it and become a more knowledgeable student. All right, let's do a couple of examples. Now, in which direction is this reaction going to go? So, it's either right or left or no direction, all right? So we've got this chemical equilibrium, we've got the equilibrium constant here, and we got some concentrations. Step 1, you want to write out the Q expression, okay? As usual, it's products over reactants, and we use the squared terms here as, we normally would, okay? Now, step 2 is to go ahead and plug it all in, right? So we want to calculate that value. So make sure you're plugging in the right numbers into the right spots, and make sure that you're squaring those numbers correctly. Please double check my own video with your own calculator to follow along. I get 6.45 times 10 to the third on my calculator. Now what we want to do is compare that number with the starting KEQ, or the KC in this case, that was given to us, okay? When you compare Q with K, we can see a 10 to the third is less than 10 to the fourth, and we can see that Q is less than KEQ. So what this means is that, well, now we want to state the direction using a full complete sentence. The reaction will proceed to the right. Okay, so that's our final answer there. Okay, let's do another practice problem here. Which direction will this reaction proceed? So we've got ammonia synthesis. Nitrogen, hydrogen are in equilibrium with ammonia, and the Kc is equal to 0.060. All right, and we've got some concentrations there in molarity for some different gases. All right, and what we want to do again is to start out by writing the reaction quotient expression. Okay, it's products over reactants. So products are on the right, reactants are always on the left, and make sure you use the squared and cubed terms there for the ammonia and hydrogen respectively. And then we have the concentrations here. So just go ahead and plug them in to the appropriate spots. And like I said, again, please use your own calculator and follow along with this YouTube video, okay? And what I get here on my calculator is 0.2 when I round it off to one significant figure, okay? Now it doesn't matter because 0.2 and 0.060 are very different. Now remember, what we want to do is compare the Q with K. In this case, our Q was calculated to be 0.2, which is greater than 0.060. So what this means is that Q is greater than KEQ. We know that now we can state the direction of the reaction. The reaction will proceed to the left, okay? And don't just write left on your worksheets. Probably write a full, complete sentence, okay? All right. So this is the summary slide once again. It's always that ratio of products to reactants. Remember that Q uses actual in-lab concentrations, where KEQ uses equilibrium concentrations that usually are measured with a spectrometer, titrations, or something like that. If Q is equal to K, no change. If Q is greater than K, go to the left. If Q is less than K, you go to the right. All right. Thanks for watching. Please like this video and please consider subscribing. Have a great day, everybody.